Hey guys, welcome to my channel. So our problem for today is we'll be learning how to do PLC programming, or the ladder diagram, famously known as. So our problem statement, which will be linked down in the description, would be we have to fill this tank up, which has three levels: LE, LA, LB, and we have to fill from LE to LA with valve A, and from LA to LB with valve B, and we have a timer. So for 5 minutes, the timer is already set for 5 minutes. So the timer for 5 minutes, we have to heat and stir the solution, and after 5 minutes, I guess there is a valve CVC which will drain out the solution. So how do we program it? So first we'll start with basic PLC and what the ladder diagram basically means. So ladder diagram is nothing but old electrical engineers trying to understand the new programming language with their old concepts of relay logic. So what they used to do in their times is they used to connect relays to control all these process equipments or automation equipments. So this is the ladder diagram, and this is the ladder diagram that was provided in the solution itself. So I will explain the ladder diagram, and I will of course point out all the mistakes that the ladder diagram has. So let's start with the first rung. So first terminology, first jargon over here is rung. So every step or every line is called as rungs. So this is rung 1, rung 2, rung 3, rung 4, and so on. So let's go to first rung. Whenever there is a PLC, there is always like L and N. So what is L and N? L means live and N means neutral. So it's like, as I said, those old engineers, for them it was like high power lines. So for that it was live and neutral. So basically positive supply and 0 volt or negative supply. So basically this is ground and this is positive supply. So how this basically functions is you connect anything in between these two lines and the device starts working. So for example, if I want to, let's say I want to start a motor. So it's like a motor. So if I connect a motor over here like this, and if I feed this program into the PLC, the motor will start working, like motor is working. Okay, but you just don't want to start the motor, right? You won't use a PLC for that. So if I want to start a motor with a push button, so I'll be having this kind of logic. So this is PB, push button, and then I have a motor N. So if I press push button, the motor will start, and if I just release the push button, the motor will stop. So that could be an example. If I want to maybe light a bulb, or maybe if I want an OR logic, so or AND logic. So for example, if I want an OR logic, so if one of my switches is pressed, my motor should start. So this is PB1 and this is PB2. So if one of them is pressed, the motor will start again. So this is just me revising the basic logics of, I guess, PLC. So motor and this, so PB1 and PB2. So if both are pressed simultaneously, then the motor will start. Each of them won't have any effect. So this is like the basics of PLC. So now we go for an important concept of PLC, that is latch. So what is latch? So if I have a push button and I want to keep the motor running, so what do I do? So in that case, we use latches. So instead of motor, now I'm going to use a control relay. So let's first understand how control relays function. So if I have one push button, and then there is this control relay CR1. So this is CR1 is basically the coil of the relay. So if I'm pressing PB1, I'm basically energizing the coil of CR1. So if I press PB1, in old days, if you were to program this by old way, you will just hear a click of the relay, that is CR1. Now if I am using CR1 to power a motor. So motor, our trusty old motor, and CR1. So these are the symbols that you will get acquainted with slowly. So this symbol means that this is the output of relay. So if CR1 is energized, this would be closed, and if CR1 is not energized, this would be open. Simple as that. Now there is another terminology in control relay, that is this CR1 again. So if I'm using the same name, that means I'm referring to that coil. So if I have this M2, so this means that when CR1 is de-energized, this would be on. So that means that if I press the push button, this switch will open up and motor 2 would be off. So effectively I've made a logic in wherein motor 1 and motor 2 would be alternatively on. So if I'm pressing PB1, motor 1 would be on. If I release PB1, motor 2 would be on. And so as the logic goes. So this is like a NOT operation with respect to the PLC. So now what if I want to latch this? So if I want to latch this, there's a common technique wherein what we can do is we can add a parallel stage here. So if I'm to add a parallel stage, I can add a parallel stage like this, or I can drag it from here too. It's just a normal circuit diagram, you can say. And I will have a control relay CR1 over here. So effectively I've created a latch. So once I press PB1, the CR1 coil would be energized, or CR1 will be actuated, you can say. If CR1 is actuated, this would be on, and then it would be energized through this path. And even if I release PB1, the coil will still be energized. So this is effectively creating a latch. So once I've energized the latch, my motor 1 would be constantly on, motor 2 won't be on ever. So and there is no way to switch this off. To switch this off, we use something called a stop button. So PB2, and over here we use this kind of switch. So notice the difference in the switch terminology. It is so simple. Like imagine there's a spring over here and spring over here. So basically what this means is this is normally closed switch NC, and this is normally open switch NO. So if I'm to press this switch, this will short and this will close. If I'm to press this switch, this will open. So normally so it is normally closed and it will open up whenever you are pressing this switch. So if you want to now we have effectively created a start button and a stop button, which you usually see in industrial automation. For example, if you are operating a drill machine, there is a red button and a green button. So green button is basically the start button, red button is the off button. So here this latch is complete now. So this is the most important part, and this is basically present in every PLC application that you will be designing for. So basically if I just press this button and this button is not touched with our normal logic, this CR1 would be on and our process would be on. Now if I want to switch the process off, what I'll do is I'll press this button down. If I press this button down, basically the contact is lost. CR1 would be de-energized or deactuated. So this relay would be deactuated. PB1 is all off. Like I'm assuming that the person has released the PB1 or the start switch. And once I leave the stop switch or PB2, the coils would still be off. So I've basically created a you can say the start stop rung that is usually used in PLC. Even over here if you see in this example, over here we are using this rung 1. So this is a rung 1. So rung 1 is basically the start stop actuation. You usually have a light bulb as an indication too. Like we use usually a light bulb over here, but it's fine if you do not use it. So if you want to use anything, do not add in series with the thing. If I want to use a light bulb, I will just use a light bulb and like this. So in parallel you can add stuff. So even here, if you see, our CR1 is like the main relay or the main control relay. So CR1. CR stands for control relay. Okay, so this is similar latch operation, and observe that every rung has a CR1 in the beginning. So that means any rung cannot be actuated without the permission of CR1. So CR1 is like the boss of our programming right now. Okay, there's a common practice wherein you can add a CR1 over here too. So CR1 over here, and this is completely correct. So that all the rest of the rungs are dependent on CR1's actuation. Okay, so let's move on to our problem that is given. So I just tear this page up so that we do not have to deal with much shit. Okay, so here in our problem we have to design this thing, and we already have a solution. So we'll just go by the solution while we draw it ourselves. Okay, so this is live and this is neutral, or positive and ground, whatever you want to take. So first we'll design our control rung. That is like absolute necessity. Even if they have not mentioned, it's better to just have a control rung. So PB1 and PB2, I've assumed it that they are start bit and stop switches, and this is our control rung. CR1, and here we have CR1's actuation coil, and that's it. So this is PB2 and this is PB1. Gosh, 11 minutes already. Okay, so this is a control rung designed. So we can use this CR1 any number of times that we want. So like let's go to other actuation. So our problem statement again is like, first we have to we'll be expecting that our tank would be at LE. So let's just assume that it is expected. Now our first rung is about LA, so this over here. So first to actuate valve VA, we are doing this. So for our first rung would be in this rung, our first part would be CR1, of course. Like without the permission of CR1, we are not doing anything. Okay. Then we'll be using not of CR5. We'll see that later. So we can add stuff later. So let's just keep a blank over here, and we can exchange these two positions. So let's just exchange the positions. Okay. So our next part is LA. So LA, and this is like a special type of switch which is also called as float. So what does float mean is these are actually pretty self-explanatory blocks. So this is like a float, the float that you have in like swimming pools kind of thing. So it's usually for level detection. So this means that if water hits this float, the switch is going to open. So until the water has not hit the float, the switch is going to be closed. So we want that, like until the chemical has not hit LA, we want the valve to be on. So and we'll have stuff in between, right? So we'll just keep that area blank, and we'll give the actuation to some other relay, CR2. Okay, so like maybe in future we can use this CR2. Then again we'll use CR1. Here we do not, for actuation of valve A now, here we do not require the CR1 stage. Like it is not absolute mandatory, because while designing CR2 we've already taken care of CR1. But you can add it, and here it is added, and there's no harm in adding, so I'm just adding it. I don't want to confuse you all. So I'm adding CR2, and this is valve A. What valve A? You can keep this blank, but now that I know that it won't be, but so yeah. So the criteria for actuation of valve A is basically CR2 being on, and for criteria of CR2 being on is the CR1 has to be on, and the water level should be below LA. So if the water level is below LA, the CR2 would be off. Other conditions would just add up, like those are AND conditions. Okay, if you have OR conditions, you can add, but I don't think in this problem statement we have any OR conditions. So now that we've done with LA, we move on to LB. So for that, we'll just assign another control relay. So CR3 maybe. Okay, that sounds good. So for CR3, same procedure, we'll have CR1, and then we have we'll have LB. Okay, LB. So this is again the float switch, and remember that this switch is above this point, so that means that once the liquid reaches the point, the switch will be open. Now another criteria in valve B is valve B should be actuated only when the solution has reached LA. So that means from LA to LB is basically the time when valve B is going to be on. So then we have to state a condition when LA or valve A is actuated, we do not want valve B to be actuated. So for valve B to be not actuated when valve A is actuated, we'll just add a not relay. So not when CR2. So that means when CR2 is on, this would be off. So that when valve A is on, this rung would be off. We'll just keep space for future CR5 or whatever that will come in. Now let's go to the next condition. The next rung is basically the same thing, CR1 and CR3, that is going to actuate valve B. You know, it is completely alright to just add valve B parallel to this and valve A parallel to this. It is like there's no harm. You can just do that. No one's going to stop you from doing that. But it's better to have it in different rungs so that easy for debugging, I guess. Okay, so now that our tank is filled till valve B position, we have to go with the third condition that is given. That is start the timer and then start the timer and heat and stir the solution. So the timer is for 5 minutes. We don't care where the timer is. The timer is given. So we have to just actuate TM. So what we'll do here is so TM should be actuated. So when is TM to be actuated? When CR2 is done with his job and CR3 is done with his job. So first is our CR1, which has to be on. Of course, it's start. And then there is CR2, which is done with its job. So no CR2 and no CR3. So if CR2 and CR3 both are off, this would be on. So that means that these three conditions should be true for the timer to be on. And we can wait for conditions, but I don't think there will be any conditions. So just connect it. Our next part is start the heater. So the heater would be started based on, of course, CR1 is there and we have our heater. So our condition for heater is, remember that heater should be on only and only when the timer is not reached. So I don't know what the timer switch default condition would be, but we'll be using this notation and I guess this should work. So this would mean that when the time is up, the switch would be open. Actually, that is not how it should be. It should be basically this wala switch, but I don't know why the notes have it. So I'm just following it. So let's assume that the timer is timer is normally closed. NC timer is NC. So when it's time up, it will be open. So if the time is up, it will be open and it will actuate the heater coil to be off. So it will be on only when the timer is on. Okay, our next rung would be the stirrer. We can add the stirrer parallel to the heater, like it's no harm in doing that, or else we can add another rung like it is added over here. No harm in doing that. I don't have space, so I'm doing that. Okay, next is again our CR1, that is central rung, and this is, I guess this is the CRS, or wait, what is this? This is the, okay, even I don't know what is this. Okay, this is CR5. Okay, yeah, this is CR5, central rung 5. So again, I guess this is where it was up. That is why it was appearing over there. So this is central rung 5. So we are assuming that when the time is up, CR5 would be actuated. So when the time is up, CR5 would be actuated. So this is NC, right? So this means that these two are basically opposite. So if this is NC, then this is NO. But usually we do not use these kind of terminologies in both the switch types in the same PLC diagram, because the person who's going to wire the PLC is going to be confused, like a hell lot confused. So we usually add a control relay over here and then add the control relays CR over here. But now that it is over here, let's not complain about it. So CR5. So CR5 is going to be on when will be on when the time is up, right? If I'm not wrong, time up. Okay, time up. So if it's time up, CR5 would be on. And I guess that's pretty much it. And there is valve C. So valve C would be open when the time is up. So basically, when everything is done and the time is up, valve C would be open. There is another parameter over here, so let's discuss that parameter too. This is valve C. Usually valves are given this symbols, but even if you write it in the circle thingy, it's fine. A lot of programmers do that. So in this we have CR1, that is our central rung, like that is the first rung, and then we have CR5. So that means that what the CR5 indicates is that the time is up and the process is completed, kind of thing. And then once CR5 is done, we have so CR5 is an indication of the time is up, like the process is done. And then we have LE. So why do we have LE, and what do we have LE? So LE means that you can say the empty valve is actuated. So over here, this is a big mistake. Like this is like no, like this is 100% wrong. So the switch shouldn't be over here, it should be over here. Okay, so I'll just tell you what this is. So that this means that the tank is empty. So once the tank is empty, so if this is a float, if this is a float, when the tank is full, this switch would be closed, right? And when the tank is empty, the switch would just open up, and if the switch opens up, it will be knowing that tank is empty, and then valve C will get closed. Now the possible improvements over here would be in this things which are hell lot of confusing, like why are we using both two things, but that's what they have used. And another thing is over here we have not defined. Okay, another thing is we forgot our CR5s over here. Okay, so why are we adding CR5s over here? So that is because there are two CR5s, I guess we've left. Yeah, two CR5s that we left. So why did we add CR5 not no CR5? Is because when CR5 is on, like when the time is up, after the time is up, our valve is basically ready to drain out the tank, right? So when the valve is draining out the tank, we do not want the valve A and valve B to be actuated. So for that purpose, we are having CR5 not over here. So if when the time's up, we do not want our valve A and valve B to be actuated, because when we are draining it, of course LB and LA are going to again sense that there is no solution, and then they will start pouring, and then it would be a huge mess. So that's to tell them that the thing is up, right? The valve is up. Another thing I must mention is for the timer, we need to add CR5 over here too. So like after the timer is like gone off, we need the timer to reset or something like that. So a reset stage needs to be added, but now that they've not mentioned a reset stage, we do not need to add it. And I guess that's it for this video. It's too long. Thank you. Please like, share, subscribe, I guess.